Hi, my name is Erica Carlson. I am a theoretical physicist at the Purdue Quantum Science and Engineering Institute. Welcome to Quantum Connections, where we have interesting conversations with people working on all things quantum. Our guest today is Dr. Eun-Ah Kim, who's a professor at Cornell University. Dr. Kim has won several awards in the field. She won some early career awards, for example, from the Department of Energy and the National Science Foundation. She's a Simons Fellow in Theoretical Physics right now. She's going to be one of the keynote speakers at a summer school coming up on harnessing the quantum matter data revolution. Welcome to the podcast, Dr. Kim.
Thank you for having me. Happy to be here.
So one of the things we'd like to hear from you is, why do you think that people are excited about all things quantum right now?
So quantum mechanics have existed since 1920s, but until recently, although we know it is an important principle that underlies visible world at a smaller scale, it was something that was very abstract and not tangible. We couldn't experience quantum mechanics of individual spins, electrons, because it's so small. Recently, the quantum computers became available to public for anybody to go and have hands-on experiences through Google, IBM, and Amazon, and that totally changes the picture. Now, what used to be very abstract can be actually experienced in using these computers that are available on the cloud. And the questions that were sort of philosophical now become a very practical question, very tangible questions. So I think quantum and quantum engineering is in sort of a very early, sort of like it just sprouted. Like it's kind of like, you have this big seed that's very promising, and you've been waiting and waiting and waiting for it to sprout. And some said it will never sprout. Some said quantum will be forever technology of future, topic of future. But it has sprouted. Now we have this early technology, early systems that are delicate like a little sprout of a big plant. But, all biggest trees start from a tiny little seed and a very delicate, tiny little sprouts. But it can grow into a big tree. And we are a lucky generation to be witnessing this moment of that sprouting. And we have the opportunity to shape how this sprout is going to grow into a big plant, what it can do for us. So it's a very exciting time.
Now, I'm curious, and I think our audience is curious too, what originally got you interested in becoming a scientist?
From when I was little, I was always interested in observing the world around me and trying to understand what's going on, right? And it was that scientific principles, especially physics, allows you to very economically understand many different things at many different scales, became really exciting to me. So going back to when I was little, growing up in Korea, when I was in elementary school, we didn't have air conditioning. So during the summer days, the way to keep us cool was to bring ice cold water that we put a water bottle in the freezer the night before. And second grade was first time I got to do this myself. First graders, mothers would do it. And now I put my bottle in the freezer. And the next morning, I found that the bottle has swollen. Like I filled it up to the brim and it had swollen. Mm-hmm. And I asked my dad, who was a professor of engineering, like, why is this happening? And he said, well, water molecules form the hydrogen bond and the molecule is bent. And he was using all this jargon. And I complained to him that, you should explain to me in the language that I can understand. If you really understood what's going on, you should be able to explain in a way that I can understand. So we had a big fight. And I ended up being not satisfied because I didn't end up understanding exactly why this was happening, except that something's very special about water. But what I did get out of that was that the notion that the properties of materials that we can feel and experience are actually controlled by what's happening at a much smaller scale that's invisible. And even though the molecule themselves are not visible and hydrogen bonds are not visible, and these require some, jargons and advanced concepts, it is possible, if I study hard enough, to understand why this is happening. That was sort of a hook that was interesting. There are other moments in my elementary school that were really important to me that left a sort of a strong memory impression in my mind. And another one of them also has to do with temperature is the experience of magnetism. So we had this experiment of rubbing bar magnet to nails, which many kids would have the experience of. So what was really fascinating happening in front of my eyes was that, I have magnet, which has red and blue. Obviously, it's a bar magnet. And I have nails, which are not sticking to anything. I rub that nail to the magnet, and all of a sudden, these nails start sticking to each other. They're magnetized. So that was already really, really cool. But then it was a cold winter day when we were doing this experiment, and we got to put these nails that are stuck together on top of our wood burning stove, which was a mechanism of heating. And in front of our eyes, these nails fell apart on top of wood burning stove. And I'm like, this is magical. Like something's happening here. First of all, rubbing the magnet to the nail made something happen to these nails. And that was undone when we heated up. And this was whole really fascinating thing that's happening in front of my eyes. And I got to understand it way later in college. That's when I decided I'm going to study condensed matter physics, because condensed matter physics explains what was always fascinating and curious to me. Another experience was of interference and optics. Um, we had rainy seasons in Korea, and we have puddles of water always in the summers, and always there's some oil floating on top, and there's rainbow color. In high school physics, um, I got to understand that there's a principle of interference underlying that rainbow, which is same as the principle that allowed us to see rainbow in my friend's hair. It's girls' high school, everybody with straight short hair, and the hair strands can actually work as what we call diffraction grating, which allows this interference to show up and different wavelengths, colors of light to reveal itself. And just sitting down and being able to put all this together into a few equations was just really exhilarating. So these kind of experiences of connecting my everyday life to something that I can understand and remember is what made me want to become a scientist, so that I can forever learn.
Very exciting, very exciting. Thanks for those stories. Of course, I love all that physics too. So I'm you're telling me about these things, and it's bringing back memories of me of the first time I saw this or the first time I saw that. I think curiosity is what drives a lot of us to be scientists. Now, you have a lot of great research going on in your lab. I know this because I'm Dr. Kim's colleague. She is a superstar in the field, so I know you've got more going on than you can tell us about. But could you tell us maybe about the thing you're most excited about right now in your research program at Cornell?
What I'm really excited about right now is how we can use classical computers and classical machines to help this sprout of quantum grow and become stronger. In other words, the quantum systems right now are noisy and small, but as they become available, that's presenting us what kind of challenges we would have in helping this sprout to become a big tree that can serve humanity. And in addressing those challenges, we are finding a lot of opportunities of bringing the classical machines' abilities to model, abilities to mine data that can help us understand what's going on in mysterious and secretive quantum systems. So this hybrid approach that which I think of as sort of a mechanism that can us help us see this sprout grow into a tree. That's really an exciting direction right now, and being able to get my hands on the latest current quantum systems data and looking at them with machine learning tools is just really fun. A lot of open questions, and always I'm trotting the water that I don't know where it is deep, how deep it gets, and it's just very it's an exploration that's exhilarating.
Well, Dr. Kim, that's all very fascinating. Thank you so much for your time today, and thanks for joining us on Quantum Connections.
Thank you for having me.